Okay, for today's lab, using buses, the first one is a ring oscillator. We haven't got a chance to cover that in the class. So the ring oscillator has to be the odd number of inverters being connected, input to output. If you look at the schematic, you can see is that 11 inverters being shorted like this, and eventually it's going to oscillate. And there's no crystal. Keep in mind, there's nothing, like even no signal input. It's just like a snake biting its tail. And how that works? So why not even number of inverters? I'll just briefly draw it over here. So if you look at, for example, 3 inverters, let's say 5, probably easier to look at. 3, 4, 5. And because we know that every inverter is going to cause a time delay, so just in case there's a voltage here, it's not either 2.5 volts or it won't be exactly 2.5 volts, just let you guys know. It won't be perfect. So the switching point at 2.5 volts is not going either up and down. So it's not forming it's called like positive feedback. So if it's a 0 here at the very beginning, and let's consider this one goes from 0 to 1, and because it's getting inverted, so there will be a time delay in between the input and output, and it will be put down to ground after a certain time delay. Okay, because the inverter has all the gates are dielectric materials, so eventually there will be a time delay. And same for this one. Whenever this one from 1 to 0, after a time delay for this gate, it will go up, right? Same for this one. After time delay will go down, even though the time delay is very short, but there's still a time delay. And then it's getting inverted. And eventually you can see this is just a 1 voltage node. Just 1 voltage node. How could you have 2 different signals? Isn't this the same wire? It's always the same wire, right? And we are assuming this one goes from 0 to 1, and on the other side of the wire it goes from 1 to 0. How could that happen? It's all because of the time delay in the middle. So it's like whenever this one goes from 0 to 1, after a goes through all the gates, it pulls it down to ground. It's still the same wire, but the thing is, it's forming a pulse like this, even though it's still the same wire, because of the time delay. If there's no time delay, it won't be possible. A wire will have the same voltage, right? Does that make sense? It's still the same wire, but at different time. Keep in mind, this is time. Okay, this is time. So at different times, the same wire will have this a little pulse being formed. And eventually, after this is being put down, it will go through the same time delay and then put up. Depending on the size of the transistors, will give you different time delay. So a bigger area of the gate will give you a bigger capacitance underneath the gate. So a bigger capacitance will give you a longer time delay. And eventually, when we are dealing with all the digital models from use the parameters from textbook, we will be able to calculate an estimate of the time delay later. But now we don't have to worry about that. Just know that there will be a time delay. And if you don't believe this, you just get a number of inverters and shorted them like this. Eventually, you'll see an oscillation like this. And you don't even need to give an initial condition. You see in the simulation, I don't give an initial condition. I don't have any input signal at any intermediate node. No input. And eventually, if you probe here, you are seeing this oscillation from 0 to 5 volts. And if you so what if you probe any of the nodes in the middle? What if you probe here? What's gonna happen? Hmm? If I probe anywhere in the middle, so now I'm probing oscillator output, right? Which is over here. It's like a ring, right? If I probe here, I'm seeing this. So what if I probe here or here or here? What's gonna happen?
Same thing but phase shift.
Same thing but phase shift. Still oscillations. It's equivalent, right? Just depending on where do you fold it. And if you grab this point and fold it that way, then this becomes the output. So it's just a phase difference, but still the same oscillation, same frequency. And there will be an equation to calculate the oscillation frequency down the road when we know all the parameters of the transistors of the C5. But now we don't have to worry about that. Just to create this ring oscillator in the schematic and do the layout. Okay, this lab is teaching you how to make a bus. So if you look at this ring oscillator has 11 inverters. However, in the schematic, you don't have to draw 11 inverters because there will be a lot of connections, can cause errors when you are manually doing that. So for almost all these EDA tools, including ElectricVLSI, it allows you to create an array of the schematic using buses. Even though they are not physically creating an array of the symbol, if you look at this one, it's just one inverter, right? Just one inverter. However, this represents 11 inverters. It's just a drawing from any of the drawing tool in my laptop. So these are just 11 inverters, but you have to name it like inverter 0 to 10. So eventually there will be 11. So ElectricVLSI can recognize this bracket. If you have a bracket after the name, it will know that it's going to be an array instead of one single symbol. And what about the connections? I mean, they all have different connections. How could you define which one is connected to where? So this one, if you create an array, it's like a bundle of inverters, right? From 1, you extend it to 10 or 11, right? And they all have their input and output. But you are only seeing one single wire here, all right? If you want to create a bus, so you can imagine that you are actually splitting that wire into 11 wires. And so we want to use a tool in the library, which is over here, the green wire, a thicker wire, and you connect that thicker wire here. I think you just left click and right click to extend it, and eventually add a port at the other end of the thick wire, and then when you name it, that's where you can define the connections. Okay, so it's following a certain order. If you look at so when you are doing the exporting, do a Control E, right? Control E, and for the export name, it follows a certain order. If you name it like this, for example, on the left-hand side, you have a first name. So the first name will be the first wires, the first inverter's inputs port name. It's similar to the concatenation of the Verilog we have been doing. Just following a certain order is like putting all these wires like a single bits together as a one longer binary number. Okay, it's the same thing. So OSC underscore out will be serving as an MSB, and then followed by 10 pins. The names are out 1, out 0, out 1 until out 9. So that binary input becomes OSC out to out 9, which is 11 bits of binary numbers. Okay, it's following a certain order. And for this one, for the output, because the first inverter's input is shorted to the last inverter's output. So if you want to make a connection between these two nodes, since we already know the first inverter's input is called what? what's the name of the first inverter's input? By looking at this. What is the name of the first inverter's input? Poor name.
And the oscillator out.
Oscillator out, right? So that's the MSB, which is the first inverter's input. Because it's following a certain order, so if you look at this one, when I name the output of the bundle here, what's the name of the first inverter's output?
Out zero.
Out zero. Okay? So the question is the first inverter's input shorted to the first inverter's output? Definitely not, because they have different names. Okay? So which inverter's output name is the same name as the first inverter's input? Tongue twister. So which inverter's output has the same name as the first inverter's input? The last one. See? I already showed you here. Concatenation, right? So the MSB for the output, the first inverter's output is L0, and the last inverter's output is OSC underscore L. And remember, in ElectricVLSI or LT-Spice, if you have the same name for the node, they are physically shorted to each other. Same as any of the PCB design tools, they have the same name of the net. It's called net in PCBs. If you have the same name of the net, they are shorted, physically shorted to each other. So the same thing here. If I name it this way, which means the first inverter's input is shorted to the last inverter's output, because they have the same name, right? And so if you look at this array here, these are the names of the inverters. So the first inverter's input has the same name as the last inverter's output. So in that case, they are physically shorted to each other, and which makes sense because I do want them to be shorted to each other to make a ring. And for the intermediate ones, you can see the first inverter's output is shorted to the second inverter's the first inverter's output is shorted to the second inverter's input, right? Because their names are both what? L0. You can tell, right? L0, L0. So eventually, am I losing anybody? No? Okay. Am I boring anybody? Just want to make sure you're getting it, okay? So if you look at 11 inverters, because they have the same name, so eventually this guy is shorted to this guy, right? Because they have the same name. And same for these ones, right? So on and so forth. Eventually this one goes to the input of the first one, okay? To form a ring. So that's how that works. When you make a bus, since you don't have the individual inverters separated from the bundle, so that's the only way you can make correct connections. It's not, you can imagine this is not only being used for this ring oscillator, but for any other applications, any other circuits, you just name it specifically. Eventually you can short that any of the wires in the bus to anywhere you want. Okay? So this one is not difficult. Create a schematic. Okay, let's follow the correct practice just in case you guys are not really following, okay? So I drew a ring oscillator like this. Eventually I think the one that I used was this one. Okay, so you guys must create a one that uses buses instead of individual ones. Even though I showed you this schematic here, but eventually you have to use this one. All right? Okay, so one quick note here. So where did you get this inverter? it is just a regular inverter, right? It's one single individual inverter. You drag it after you create the icon view, and you drag it to your ring oscillator's schematic. So drag it from the left to the right, and then connect to a bus, and rename it to make it an array. For the layout, same thing. You drag it into the ring oscillator. So this is the inverter's layout view. You drag it into your ring oscillator's layout view, and you make an array out of it. So my question is, can you rename this layout? Can you rename this layout to make an array, like the schematic? You create a bus to the layout, and you rename it to bracket 0 to 10. Why?
Because it's a layout view. You have to.
It's the physical layout, right? Everything shows up in the layout view will be printed on the wafer. Okay, how could you make a bus and everything overlapped on each other array? It doesn't work. It's a physical drawing, okay, of the engineering design. So eventually you have to create an array. When you create an array, it's a physical array instead of a symbol, right? So buses are not working here. So it has to be a physical array. And then you'll make the connections of the top and bottom rails, and connect output to input, input to output, and eventually ring, close the loop because all these are metal ones. So if you want to close a loop, it's better to drill a hole to the top to metal 2 and make the connection. So you don't have to route it above the top rail. Because there's no way that you can drill a metal 1 wire in the middle, because there are just so many different things in the middle can potentially cause a short circuit. Because there are just so many things. One quick question: can you drill a metal 1 on the top of this guy? Why or why not? Can you let the metal 1 trace run across the transistors? Really? So what I meant was, if I lay out like this, right? I'm having my metal 1 go through like this. Yeah, blue's metal 1. But if I don't have metal 1 here, right? If I don't have metal 1, just a transistor. So for example, this one. It's not a good example as well. So what I want to say is, you're not supposed to do that, because these are vias, right? So these vias are what? Via 1. Via 1 is a through hole directly connects to metal 1. So these, remember when you place a transistor over here, the vias are already existing, right? You cannot get rid of vias. So even though you don't have a metal 1 wire on it, but these vias are metal 1 vias. Or probably not directly metal 1, but it's the via, usually aluminum, in the middle, directly shorted to metal 1. So if you run the metal 1 on the top of the via, they are connected. So you are basically connecting to the P plus of the transistor. So it's not allowed. So in that case, do you really have any space to run metal 1 in this area at all? No, nowhere. Because nowhere here, definitely nowhere here. Here, not allowed. Here, not allowed. So you don't have any room to run metal 1 in the middle. So in that case, if you want to close the loop and make a ring, it has to be metal 2 or metal 3, right? So that is why you need a little node. So this is the technique to introduce metal 2 into a circuit, which is you create. So these are vias, right? These are metal 1 to metal 2 vias. You drag a via and place it here, because this is the metal 1 to metal 2 via, so it's able to connect it to metal 1 and metal 2. So you drag a little via here, and you left click and right click, make a connection to the metal 1 wire here for the input of the first one, and you do the same thing for the output of the last one, and eventually you introduce the metal 2 in the middle, which is not going to affect anything because it's on the top. So that's how I did it. And you can see the pure purple colors are just the metal 2 without anything underneath it. So that's why it's showing a pure purple color. And the ones is a little bit darker is overlap of the metal 2 and metal 1, but which is fine. There's no direct connection if you don't have a via, because they're on the different layers, right? But for this example, they are shorted to each other. So this is the layout of the ring oscillator, and eventually it looks like this. And because you are not really using any of the intermediate pores, so we can just use one final output as the output. So later on, when we introduce some of the math to calculate the time delay or the ring oscillator's frequency, the oscillation frequency of the ring oscillator, we will be able to see how fast it could be. But eventually, it's very difficult to create super fast oscillations using crystal. Requires special materials, and that is why on chip, usually in integrated circuits, for very high speed circuits, we usually use ring oscillators to provide a clock. For example, high speed camera, right? It's having maybe 100,000 frames per second, right? A lot of times they use ring oscillators to create the shutter's signal. So it has a lot of applications because you can run it really fast. And task 2 is for NAND gates, but it's 8 bits. So you can imagine you have to use the same technique, create a bus, make an array. You can tell that I'm creating an array out of it. It's an AND bracket array. Same concept, but the thing is, they are not interconnected, which makes sense. It's basically an array of 8 NAND gates in parallel, right? You are not expecting any of them being shorted together. They're just individual NAND gates. However, when you probe it, because every single input, a bus, has 8 inputs or 8 wires, 8 signal lines. So ElectricVLSI gives you several components in the toolbox. So this one, J, is called junction. It's a junction. So this is able to short all these 8 wires in the bus. If you connect that thick green bus to the junction tool, and eventually all these 8 wires will be shorted together. You don't have to do anything else. And they will be physically shorted to each other eventually. So you can see here, I put a junction here, and then I connect this green wire to the junction, okay? And it becomes one wire. Because it becomes one wire as a junction, I can directly use just one single wire and connect to ground, connect to VDD. So I can use this technique to short all the inputs, one of the inputs of the AND gates to VDD. So I'm giving a 1 signal to all the inputs of the AND gates. And for the other input, you can see I want to give different signals for each signal line in the bus. And the way to do that is using this little node tool in the toolbox. You have to place them over here one by one. Since I have 8 of them, so I have 8 little dots. And then you introduce that bus wire and to connect to every single one of them and short them together like this. All right? And the way you differentiate in between all these signal lines from the bus is you name them differently. So after you short all the little dots to the bus, you introduce a single wire out of it and select that wire and do a Control I. Change the name of the arc. It's called arc. So all the blue wires, single wires, are called arcs in ElectricVLSI. And you do a Control I to change the name of the arc. If you name it B0, then it represents the B0 of the bus, right? Just do it so on and so forth. Just rename every single one and give them a different signal. So the reason I'm doing this is I'm trying to simulate, give the AND gates some combinations of the inputs and to simulate the outputs. So you can see I'm giving 4 of the AND gates inputs 1s and 4 of them 0s, but for the all the rest inputs of the 8 AND gates, I give them all ones. So you can imagine for the output, there will be 4 ones and 4 zeros eventually. And if you look at the simulation, and they are 4 0 and 4 ones, so you can verify the functionality of the AND gate. Just disregard the 6 point something nanovolts. It's like almost 0 volts, right? Blah, blah, blah. So if you see like nanovolts, it's basically 0 volts. So 0 volts, 5 volts, 0 volts, 5 volts, 0 volts, 5 volts, 0 volts, 5 volts. Okay? So the AND gate logic is verified. Even though it's not exploring all the possible combinations of the inputs, but which is fine. We know it works. So if I change the junction signal to 0 to ground, okay, this is gonna clear. It's gonna clear all the outputs. It's gonna reset all the outputs to 0 volts, which makes sense because 0 and everything is gonna be 0. And this is the layout. So every time you introduce the metal tool, you want to connect, place the little metal 1 to metal 2 via here first, and then click that specific metals tool in the toolbox, and then do the connections. See here, metal 2, metal 1 to metal 2 via. I did a metal 1 connection to the poly to metal 1, which makes sense because metal 1 to metal 2 is here, metal 1 to metal 2 via, and poly to metal 1 via is here. So that's why they are interconnected from poly to metal 1 and metal 1 to metal 2. So they are connected. That's why I can directly use metal 1 to short these 2 vias. These 2, okay? These 2, which is over here. And then after that, I introduce the metal 2. So do metal 1 first. So it's drilling a hole from poly to metal 1, and then drill another hole from metal 1 to metal 2. And eventually get a purple wire. So the reason I'm doing this is, so these are AND gates inputs. These are the inputs. You can see these are all the A's, A0 to A7. And I introduced all the B's on the top. So these are B0 to B7. And I introduced all the outputs on the top as well, but it's your choice, right? You can do it in a different way. No problem. Similar to the OR gates. The last one is NOR gate. I think it's a NOR gate, right? NAND gates. Okay. So if you get the first one, the second one done, I think the follow ones are pretty simple, I believe. And also make sure they are in the same height. You can easily use a ruler tool in ElectricVLSI to measure it before you place them. Eventually, we want to keep the same height for the rail-to-rail gap, the distance in between the two power rails. Okay. All right. Any questions on this? No. Okay. Can get started.